So I'm going to introduce Guanqiao Mao, who is the new head of the School of Engineering, in order to introduce the lecture.
Thank you.
Thanks, Ian. So since I'm new, I have to say I must admit that this was written by James Hopgood and Ian Underwood. Okay, so if there are any bad jokes, it's their fault. It is my great pleasure to introduce Professor Colin Cunningham, who has enjoyed a highly distinguished career as one of the world's leading astronomical researchers. In 1987, Colin joined the forerunner to the UK Astronomy Technology Centre, ATC, the Royal Observatory of Edinburgh as project manager for the Submillimetre common user bolometer array, also called SCUBA. The receiver is at the heart of the James Clark Maxwell Telescope in Hawaii. SCUBA ranked second only to the Hubble Space Telescope in terms of citations between 1997 and 2003. The SCUBA team was presented with a Team Achievement Award by the Royal Astronomical Society in 2009. SCUBA is to this day on display in the National Museum of Scotland in Edinburgh. And I was told if you ask Colin nicely, he may offer you a guided tour. Incidentally, the development of its successor, SCUBA 2, involved intense collaboration among the ATC, the Scottish Microelectronics Centre under Professor Anthony Wharton and others. Colin moved on to a range of roles of rising seniority within the ATC and on multi-partner projects. For example, from 2005 to 2016, he was principal investigator for the 88 million pounds UK Extremely Large Telescope. He then relaxed into partial retirement, involving a more wide-ranging role within the ATC alongside time to think outside the ATC box. Colin and Ian Underwood submitted a proposal to the Royal Academy of Engineering to fund a visiting professor position in innovation, instrumentation, and systems engineering, with a remit to embed systems engineering within the engineering curriculum. Thank you. The project was a great success and led to Colin's contract being expanded and extended to the present day. Highlights of Colin's time at our school include developing a fourth-year interdisciplinary group design project with Professor Rebecca Chung, contributing a course on systems thinking, systems practice to the new MSc in leading major programs. Hijacking Jonathan Terry's fourth-year course on professional issues, so that half of the content is now systems engineering. And with that, it gives me great pleasure to invite Professor Cunningham to deliver his valedictory lecture, Space Telescopes from Science Fiction to Reality and Back.
Thank you very much, Colin James. Okay, so this evening I'm going to take you on a journey through space and time. We're going to start in the 1920s in Weimar, Germany, to discover the origins of ideas about space telescopes. And then we're going to go up towards this present day and look at things like the Hubble Space Telescope and the James Webb Space Telescope and how they've been such a great success. And from then, we're going to look at what's planned for the relatively near future. And then after that, we're going to perhaps get back to science fiction, because we're going to be talking about what might be possible within the next 100 years. And if we think about how far we've got since 1929 to 2024, maybe lots of things are possible. Okay, so I'm going to start with the James Webb Space Telescope, which was launched on Christmas Day 2021. And Alistair Glass is sitting in this audience. We had an enormous role in the instrument that we're going to talk about on this telescope. So if you've got any awkward questions, you can go and ask him over a glass of wine. Anyway, it's a huge telescope, 6.5 meters in diameter, made out of segments of beryllium gold-coated beryllium, and with this strange, does this work? Does this work? Yes, this strange thing here, which is a sun shield the size of a tennis court, which keeps the heat of the sun and the Earth off the telescope to allow it to cool down. And we'll get into why a bit later. So this was Christmas Day 2021, and this is the launch of the Ariane 6 with James Webb on it. And you can see it's in French because Ariane is a French company, and this was from French Guiana.
From a tropical rainforest to the edge of time itself, James Webb begins a voyage back to the birth of the universe.
I didn't write the script.
Punching a hole through the clouds, 20 seconds into the flight, good pitch program reported. And let's go down to the floor in the Jupiter Control Center to Raphael Chevrier of Arianespace. Raphael, so far so good.
Hi Rob, so far so good. Everything is nominal, as we say when attitude and trajectory of the Ariane 5 is going perfectly well, as you can see also on the...
Yeah, this is the interesting thing because it's following the expected trajectory absolutely perfectly, and that's going to be important.
We'll be sending commands to prepare James Webb for the initial series of commissioning activities of electrical power for the telescope. James Webb, of course, will be...
And this is the last thing we've seen of it. Go Webb. Great, a great time. But the interesting thing about this is the last thing that anybody on Earth will see of this telescope. So it's off. And all this exciting stuff happens to it while it's on its way to where it's going, which we'll talk about in a second. So it all has to unfold because it would never have fitted inside the nose cone of the rocket. So you can see this huge sun shield starting to be opened. This is several layers of very thin plastic coated with aluminium, very, very delicate. So that was a scary moment when we were waiting for that to happen. And it wouldn't have cooled down without that, so it would have been useless. And in fact, people always say, but there are 344 single points of failure in the James Webb Space Telescope. We normally, with space projects, try to have duplication of everything and redundancy. So there were 344 things that could have gone wrong and then it wouldn't have worked. So, but they didn't, amazingly. So this is a fantastic achievement by ESA and NASA and the Canadian Space Agency. And we should see in a minute, we should see the secondary mirror start to deploy. There it is. And obviously without that it wouldn't work either. And then these three mirrors also pop out, and there it is. So it's there. So it was on its way to where it's going, which is this place. So it's a long way from the Earth. It's 1.5 million kilometres from the Earth in what's called the Lagrangian 2 orbit, and it follows behind the Moon and the Earth and goes around the Sun. So it's always got the Earth and the Moon and the Sun on the correct side of the sun shield to keep it cool. And what's he actually doing? We're going to find out why it's in space a bit later. But the important, it's basically measuring light. And light is electromagnetic radiation, and it goes a very long way. It's very varied. It starts off with very high energy gamma rays and X-rays, very short wavelength, through the ultraviolet, and then this little bit here, which we can see, visible light, and then there's a whole load of infrared stuff, and then we get into microwaves and radio, very long wavelengths. So the Webb telescope actually goes quite a long way into the infrared, actually up to 28 microns. We can only see up to, 7.7 of a micron, so it's 28 times, 30 times longer wavelength than we can see, which is important. And it's important for this reason, because what we want to do is actually do chemistry in space. So this is called spectroscopy, and this is where we look at the light that's coming from an object like a galaxy in this case, and measure its irradiation over a range of different wavelengths or colours. And if you do that, you end up with a spectrum, and then you can look at the spectrum and you can do chemistry and you can work out what it's made of. In this case, it's got lots of hydrogen of different types, neon, oxygen, more oxygen, and you can work out lots about what's going on to this galaxy, which is amazing because it's possibly one we're looking back in time 13.1 billion years, which is a hard number to get your head around. So this is right at the beginning of when galaxies and stars started to form and started to emit light. So it's a time machine. Now the science instruments, I'll go over this fairly quickly, but there are 4 of them that actually do this. Most of them have got cameras and spectroscopes in them. So there's 4. There's one called, just a minute, one called NIRSpec. They're very boringly named. NIRSpec, the Near Infrared Spectrometer. This was basically led from ESA with some American content as well. And there's a fast guiding sensor, a near infrared slitless spectrometer, which I won't explain. That was built by the Canadians. And then there's NIRCam, which was built by a US consortium. And most importantly to us in Edinburgh, MIRI, the mid-infrared instrument, which was led by, from the UK ATC, and was actually led by Gillian Wright, who I don't think's here actually, but anyway, so she won't be embarrassed. So this is Gillian receiving a medal last year, the Caroline Herschel Medal, which is a joint medal presented by the Royal Astronomical Society and equivalent in Germany. And it was given to her because of the immense leadership she did on this project over 20 years, and amazingly successful. Very, very determined lady is Gillian, and she needed to be, because she was running a partnership which was like this. There's something like, what's the number, 23 organisations across Europe and the US. So she was responsible for the European side of this, all around Europe. And you can imagine what it's like coordinating all this and delivering everything on time and getting it all work together. So that's it. So the instrument itself is quite complex. Did I miss something there? I think I did. No, I didn't. Yes, I did. I mismentioned Alistair, who's sitting there. So not only was Gillian a leading part of this project, Alistair was the instrument scientist, and he led the whole commissioning team at NASA Goddard, and which he tells me was such a wonderful experience because the team was so amazing, and he did a fantastic job as well. He won't say that. But anyway, and we also had the optical lead and the mechanical lead at Edinburgh. So a lot of the success of this is due to the team at the Royal Observatory as it was when it started, and then the UK Astronomy Technology Centre. Okay, so this is, I'm not going to go through the optics of it because it's really complicated, but it has to be because it's got to fit a lot of stuff into a small space. To work at this mid-infrared wavelengths from 5 to 28 microns, and it does imaging, it does low resolution spectroscopy, medium resolution, and also something called integral field spectroscopy, which would take me another 10 minutes to explain, so I won't. And coronography, which is, I will mention slightly, because coronography enables you to look at very dim objects that are next to very bright objects. So it's a bit like holding your thumb against the sun, and then if you do that, you can possibly see something next to it. Now, I don't recommend doing that, but this is the equivalent, so that you put up a mask, and then next to the mask, you can get images and spectroscopy of a planet that might be next to a star. So this is going to be important as we get through the lecture. So this was all commissioned together at the Rutherford Appleton Laboratory, and this is it in its clean room being tested quite a long time ago. Can't remember, when was it? 2010, yes. So these projects are very long. So this was great as well. And it turned out that this of the 4 instruments, this was the first one to get delivered. So that was another great achievement. Now, when you know, it takes a long time to get a big mission like this to be accepted. And of course, you need a science case. What's it going to do? And these were the areas that were identified at the beginning. So one is looking right back in time, like we saw that galaxy at 13.8 billion years, or maybe a bit less than that, but when stars and galaxies are forming. And then understanding how those galaxies and the black holes that live at the centre of them actually form and evolve. Then the life cycle of stars from their birth to death. Looking at planetary systems, including our solar system, how they form and evolve. And then finally, studying exoplanets. So these are the planets that are around stars relatively nearby usually, because they need to be in order to see them. And we'll talk about that a bit later, but that's the one I think is probably the most exciting aspect. And of course, this has been fantastically successful. In the sort of basically 2 years that it's been in operation, you can just look at these major journals and see that the impact has been enormous, and wonderful pictures as well. But most importantly, a fantastic amount of science. Now, before the James Webb Space Telescope, there was this one, which is called the Herschel Space Observatory. So I'm very proud of this one because I worked on this one. So I was the systems engineer on the one of the instruments called SPIRE, and we also built a high precision beam steering mirror up in Edinburgh as well. Now this is a bit different because it's 3.5 meters in diameter, so it's pretty big, but all in one piece. So instead of lots of segments, it was launched like it is, and it was also launched cold. So it's cooled to 4 degrees Kelvin using liquid helium and then launched. So it's quite a scary process, but that worked really well too. So that was the biggest space telescope before the James Webb. Right, okay, so that's where we are now. But where did we start from? And this is going back into the 1920s in Weimar, Germany. Right, so it was first proposed in 1923 by Hermann Oberth. Now I'm guessing, if I ask you all, how many people have heard of Hermann Oberth? One. Golly good. That's great. I expected that. So Hermann Oberth was an interesting guy. So he proposed this in a thesis or a book. Well, it was a thesis. It was his PhD thesis, effectively, or the equivalent in Germany. He actually was of German origin, but was born in Transylvania, in Romania, and he came to Germany, and they refused to give him his doctorate because they thought his ideas were far too outlandish. So he also went, after the war, he ended up moving to America with all the other people that came out of the various rocket projects in Germany, which we'll mention in a minute. And he went to work with the Army, the US Army Ballistic Missile Agency. And you can see here was his protege, who was Wernher von Braun. But I think quite a few people have heard of Wernher von Braun. So Wernher von Braun was the guy who was taken by the Americans, and they kind of forgot about his history with the Nazis and the way he used slave labour to run the Peenemünde factory to build the V2 rockets, and turned him into a nice, friendly US citizen. Anyway, so what did Hermann Oberth do? Actually, the other thing about Hermann Oberth, it was kind of weird, because not only did he have mad ideas about rockets, which turned out not to be too mad, he also supported claims of flying saucers in the 50s, and he later went back to Germany and got involved in some very dodgy right-wing politics, so maybe not such a pleasant character either. Anyway, so he wrote this book called The Rocket to Planetary Spaces, which was in 1923, and you can actually read it on the internet because NASA translated it a long time later. And this is what he said.
A large concave mirror which could be moved into place from the observer's cabin by means of 3 elastic steel wires wound on drums that served as the lens of a large telescope. A small telescope in the observer's cabin served as an eyepiece. We did not need a pub dark on the inside, for the sky was completely black. Just as little did we need heavy supports on which to fasten the telescope, for the single parts had no weight. They remained in relation to each other just as we put them. Here the mighty installations were superfluous that are needed on Earth to support and carry the whole. The telescope magnified 100,000-fold, a magnification we could afford, for there was no flickering atmosphere.
So this is the kind of idea we're going to come back to. So the idea that you could build a telescope in space and you could make it very lightweight because it doesn't have to deal with gravity. And also the fact that you've got no atmosphere so you can get very good images. So this is basically what's been done. It's kind of weird the way he describes it. But anyway, and it's amazing that I managed to get a recording of his voice from 1923, isn't it? Obviously a fake. Right, the next chap is also interesting. So he was called Hermann Potočnik, and he was born in what's now Croatia, and he was a captain in the Austro-Hungarian army in the First World War, and he was, for some reason, he published under the name of Hermann Nordung. I can't find out why, and he wrote this book problem of space travel, the rocket motor. And this was a little bit later than Obert. But in this book, which you can again read online, he proposed multi-stage rockets, space stations, spacesuits, radio communications, and space telescopes. And it was publicised in this Science Wonder Stories journal in whenever it was. And you can read that as well. And he talks about, again, mirrors that are flying about in space, supported by wires. So it's pretty much like Obert's idea. And I don't quite understand what the astronauts are doing in this clothing. The personal protective equipment seems to be dark glasses, and that's it. But still, this is amazing, and it's a science wonder story, isn't it? Okay, so a bit later on, 1940, another of these slightly crazy popular science fiction magazines called Astounding has got this article in it, called The Lunar Observatory No. 1 by R.S. Richardson. I'll blow it up for you. So, a professional astronomer suggests detailed plans of what would be needed in an astronomical observatory on the moon. Okay, on the moon, eh? So that's another idea. So here he is, Robert Shirley Richardson, who also had an alias because he wrote science fiction books as well. And
Peering ahead, we can see the astronomer of tomorrow making routine trips back and forth between his comfortable office on Earth, with its computing force, library, and lecture rooms, and the observatory itself on the moon.
Okay, so I can see Alistair giggling at this point. So remember that the computing force at this time was a load of women in a room with calculating machines. They didn't have any computers, and obviously they wouldn't be able to remotely operate a telescope. But this was the idea. So again, this is an interesting idea. So putting an observatory on the moon. Let's talk about that for a while. So to do that, we need to go back to science fiction. So this is, people might be familiar with this film called Metropolis from 1927, directed by Fritz Lang, but written by his wife, actually, Thea von Harbour. And it's probably the first film to actually highlight the dangers of artificial intelligence. We've got this robot here, looking very splendid. It's obviously a silent film, but you can read lots into it, and it was actually distinctly anti-fascist. In fact, quite soon after that, obviously the rise of the Nazis happened, and Fritz Lang was 50% Jewish, and obviously he had this sort of anti-fascist feel, and he decided it was a good idea to leave Germany and go to Hollywood. So he became a very successful director in Hollywood, and Thea stayed behind and joined the Nazi Party. So interesting. But they made a film as well as Metropolis, which is called Frau im Mond, Woman on the Moon. And this was a couple of years later, and I'm going to show you a little sequence from this that's been colorized. Special effects are not great, but remember when it was. So the time is ticking over. It's pretty much like the James Webb Space Telescope launch, really. Maybe a bit more steampunk. But this is actually the first time that anybody ever showed a countdown, which we still do. So I think she looks a bit worried. And we seem to have Leon Trotsky here with a mouse, alongside what looks like Adolf Hitler, actually. But anyway, so off it goes. Time's coming down, 20 seconds to go. Take a deep breath. That's going to help a lot, isn't it? Yeah, again, there's very little personal protective equipment. But you notice there's these hooks on the floor. They're to hook you down so you can walk about when you get into no gravity. So here we are, ready to launch. 10 seconds to go. And we've got a countdown coming up. So, as I say, this is the first time anybody used a countdown. 4, 3, 2, 1. Now! And off it goes. Again, graphics have improved a bit, but off it goes into space. And we're now getting into another scary moment where he's trying to separate the two stages. So the second, we've lost all the power from the first stage, but the second stage is working. So this is actually pretty much like we still launch most spacecraft. And the reason it's quite accurate is that Hermann Oberth worked as a consultant on the film. Okay, so now to get a little bit more serious. So in 1946, Lyman Spitzer proposed that we should think about advantages of an extraterrestrial observatory, a space telescope. He described a telescope that would observe wavelengths not easily seen, so the ones we saw before, like gamma rays and far infrared and X-rays and ultraviolet, beyond the limitations of the Earth's atmosphere. A space telescope could get higher quality images and see further into unimagined parts of space. A simple idea, really. Also mentioned by Henry King in this great book that I've got a copy of called The History of the Telescope from 1955. Thus we return to the old problem of escaping from the damaging optical effects of the Earth's atmosphere. And there is no escape as yet. In the future, when interplanetary travel becomes possible, observing stations and ultimately observatories may be established in space. So it's all been proposed coming up to the 1950s, and what we need is the technology to do it. So the technology to do it came from Wernher von Braun. So here he is with some of his Nazi friends, not very nice. And this is the V2 rocket. Of course, the V2 rockets were picked up by the Americans and brought back to America alongside Wernher von Braun and Hermann Oberth and lots of other people. And this is the this is the V2 rocket, which is fueled by a mixture of liquid hydrogen and alcohol, a bit like we're going to do after the meal, the conference. Anyway, and this is actually what Oberth wasn't very happy about. He thought it should be a solid fuel, so they fell out actually. And but when the Americans got hold of it, they decided, okay, well, we can use some of this for the Cold War, but we can also put some instruments in it. So they built a solar spectrograph to do ultraviolet spectroscopy of the sun, and that was done in 1946, so pretty soon after the war. So this was really the first space telescope. And then, of course, the Russians got very excited and produced Sputnik, which terrified the Americans. Geopolitical earthquake fundamentally changed the way we look at science and science funding. And the effect of that was for the Americans to set up NASA. Meanwhile, the Russians were busy. They were working on lunar probes, most of which didn't work. They had 6 attempts at soft landing on the moon, and none of them worked. At this time, anyway, by 1965. But one of them actually did, while it was in Earth orbit, it actually started to do some astronomy. So it measured the gamma ray background flux density, so right at that high energy end of the spectrum. And the Americans decided they'd try and do that as well, so they built a gamma ray telescope and launched that. So it started happening in the 1960s. But of course, the thing that was stimulating all this wasn't because people were interested in science. It was because people were worried about the threat to America from the Russians. And what they did to circumvent this was to build spy satellites. How am I doing for time? Okay, yeah. So they built 16 what were called keyhole military images between 1976 and 2013. And I think most people that worked in astronomy didn't actually know about these things, were pretty secret. But if you look at it, this is now in the Smithsonian Museum in Washington. It looks extremely like the Hubble Space Telescope. And in fact, it used the same design of mirrors, which will lead us to another issue in a minute. So the Hubble Space Telescope, which used a lot of the technology from the keyholes, was launched in 1990. And some of you are probably old enough to remember that this was a kind of a disaster, because when it was launched, this was a sort of image that was produced. So there was spherical aberration in it, and it was all out of focus. It was fixed and ended up looking like this, but it took an awful lot of money and time. So there were lots of unpleasant publicity for NASA, like this one. The taxpayers getting slightly irate. And but the reason, it's interesting, there are technical reasons why this happened, and there are also programmatic ones. So the technical one is that the mirror, this 2.6 metre mirror, 2.4 metre mirror, sorry, was actually 4,000th of a millimetre. Sorry, yeah, 4,000 of a millimetre, too flat at the edges, so it was sort of levelled off. That doesn't sound very much, but actually we generally try and get to errors of 1/10 of a wavelength in astronomy for instruments and telescopes, and that will be 30 nanometres, so that's a lot. This is way out of spec, and that's why the images were totally useless. And the project shows that the error that could have been stopped in the design stage, actually the design of the testing phase, could have saved $1 billion by £10 million of work. And the James Webb Space Telescope took this on board, and as I'll still tell you, the testing on the JWST was incredible. The whole thing was tested end to end and at low temperature. So apart from maybe the sun shield, which is pretty hard to do. So lessons were learned, but how did that happen? So I'm going to get a bit technical now. So you measure mirrors by using something called interferometry. And if this is a spherical mirror, this one that's been tested here, what you do is you shine a laser through some optics through a reference surface, which is also a sphere, and then you get the light bounces backwards and forwards and is taken to a detector, and you get interference, and that gives you this nice straight lines if everything's working well. Now you can also do the same thing with a non-spherical mirror by using something called a null corrector, which I won't describe. But it allows you to look at something that's not a sphere, which is what the Hubble telescope mirror was. And the problem with the measurement was as simple as a little bit of paint that had chipped off a field cap. So one of the issues with the Hubble was it sat around for years because of the Challenger disaster. So NASA weren't able to launch it. And during this time, the paint on this, the anti-reflection coating, or paint, on this little piece got chipped and nobody noticed. Nobody noticed because they wouldn't let NASA in because it was a military facility. So lots of different reasons for this. So what happened was, instead of the laser shining off the end of this metal bit, this metering rod, it reflected off this little chip bit here. And it was 1.3 millimeters out, and that was enough to make the mirror useless. So that's interesting, and it's not just a technical issue, it's to do with the programmatics of the mission. Well, of course it was fixed, and we got fantastic images, and everybody's kind of forgotten about the problems just about now because it was so great, and it still is. Okay, so that's the Hubble telescope. And the Hubble telescope is interestingly different from the James Webb, because the mirror, the 2.4 metre mirror, is warm. It's at 21 degrees, so it's pretty much the same as this room. And that's fine for looking at visible light, but not very good for looking at infrared. And to look at infrared, you need to cool the telescope. So the JWST is cooled to 40 degrees above absolute zero. That's minus 233 Celsius. So very, very cold. And the reason for that is that anything that's warm would emit so much thermal radiation that you wouldn't be able to see the astronomical objects in the infrared. You just see the telescope, so that's why it has to be cold. Right, this takes us back to Mr. Nordung, or Mr. Potocznik, because in his thesis he said it would also be possible to produce not only extremely low temperatures more easily than on Earth, but also come to this at the same time much nearer to absolute zero. Not quite true, but anyway. In an observatory in space, besides the usual process of helium liquefaction, there would be available a possibility of most extensive chilling by radiation into space. So 1929, this is the principle of the Hubble, of the James Webb Space Telescope. The actual work that went to actually make this happen came out of Edinburgh as well. So in 1993, and a bit earlier as well, there was another proposal. There was a proposal for an international infrared space observatory that would be cooled by radiation to space, called Edison. And it came out of an idea and lots of work by sadly departed one of my great friends, Tim Harden, who went around Europe and the US berating people that this was a great idea, that you could cool the telescope just by radiation to space. And eventually, this was accepted, and that's what became the James Webb Space Telescope. And obviously Tim was awarded a medal by NASA for this. Unfortunately, after he died, and he had to get, in fact, John Mather, Nobel laureate, was presented with the medal on his behalf. Okay, so that's passive cooling in order to get this telescope to 40 degrees above absolute zero. The next question is, why do we want to build big telescopes at all? What's the advantage? Well, the first one is bigger telescopes get a lot more light. So it's like your eye, the pupil of your eye, as it expands, it allows more light in. The same thing happens with telescopes. The sensitivity is proportional to the area of the telescope. So an 8-metre telescope on the ground would be 1,000,000 times more sensitive than the human eye, even if it was dark adapted. And as you double the size of the telescope, you get 16 times brighter images. So you get a big advantage from a bigger telescope. The other thing you do is you are able to see more detail. So out into space, you can see things you couldn't see on the ground. Again, this is a little bit technical, I'm afraid, but we'll see if we can get through it. So the properties of light are such, because it's a wave, that if you take a point source like a star and focus it onto a camera, you don't get a point. You get what's called a diffraction disk or an airy disk, which has got a very bright centre and lots of rings around the outside, so that you can't do anything about that. And this limits the resolution of the telescope, the detail that you can see. So if you look at the shape of this thing and you bring two objects closer and closer together, eventually they get to a stage where they merge and you can't see them anymore. And this is called the diffraction limit, and it's proportional to the wavelength. So the longer the wavelength, the less detail you can see, but also it's proportional to 1 over the diameter. So the bigger the telescope is, the more detail you can see. So what does that mean? If you took a telescope on the ground and looked at the moon, an 8-metre telescope would be able to resolve, as we call it, 28 metres. A 39-metre telescope would resolve 5 metres, which is 4 milliarc seconds. Now, what's a milliarc second? A milliarc second is a thousandth of an arc second. An arc second is a 60th of a arc minute, and an arc minute's a 60th of a degree. So it's a very small thing. Again, it's quite hard to get your head around, but this is an example. So I have a penny. So if we took a penny and we were to put it at John O'Groats and have a telescope of 39 metres in diameter at Land's End, it will be able to resolve two things that were as far apart as the diameter of that penny. Of course, you won't be able to see the picture on the penny. So that's an idea of what this means when you start to think about the resolution of a telescope and why you need bigger and bigger telescopes. So the next question is, why do you want... Obviously, this isn't going to be very good. You're not going to be able to see anything on the ground because of the curvature of the Earth and the atmosphere. So why do you want to go into space? Well, this is one reason, the atmosphere, as I just said. So the atmosphere is a very thin layer around the Earth, but it causes a lot of trouble for astronomical observations. The reason it causes trouble is that the air moves around and it's like lots of little lenses, and as they move around, the image of the star moves around as well. So this is twinkling, and you can get rid of this by something called adaptive optics, but it's never totally perfect. So you really want to go into space, and you also want to go into space because of this thing we talked about before about the light being across a great swathe of wavelengths, and only a small amount of those actual wavelengths get to the Earth, like visible light, some infrared, and lots of radio, but everything else, like gamma rays and X-rays and long infrared, can't be seen. So we have to go into space telescopes. Okay, that's enough of the technical bit. The James Webb Space Telescope is now coming with some amazing results. I'm going to mention just one of them. So this is an image of a supernova remnant, Cassiopeia A. So this is a star that exploded in the 17th century, and there's all sorts of exciting things going on at the centre of this. There's lots of other things going around it which can be seen by this MIRI instrument, which looks at dust, at relatively warm dust. And this is all the remnants of the stuff that's come out of an exploding star. Now, people always say, of course, that the things that come out of exploding stars are the things that make us, because all the elements like iron and oxygen and so on that come out that make life actually came from these supernovae. So actually that's an amazing image from using MIRI. This is an image which takes a combination of X-rays and optical and infrared, and both from Hubble and from the James Webb Space Telescope. And you can see there's an awful lot going on. Right at the centre of this is the remnant of what happened to the star. So that's a neutron star that's very, very heavy, and there's all sorts of mass ejection. So this sort of image would keep astronomers busy for a very long time, trying to understand what's going on. Right, okay, so that's where we are now. We've got these sort of images coming out. The James Webb Space Telescope is going to work for probably up to 15 years. The design life was only 5, but because ESA and Ariane did such a good job at launching it, they used very little of the propellant, so it was able to keep going. Okay, so now we're going to talk about what's going to happen in the future. So there's some plans already. One's called the Nancy Grace Roman Telescope, which is actually using one of these spare mirrors from the Keyhole program. But it's got a much more field of view than the James Webb Space Telescope. It's named after Nancy Grace Roman. It's shown here next to a model of the Hubble, and she was really one of the pioneers of the Hubble Space Telescope, so it's great it's been named after her. This is what it's going to do, much bigger field of view than the Webb, so that it will be very useful for astronomers to actually understand a wider what's going on in the universe, and the Webb can look at more detail. So that's being built at the moment. There are lots of ideas for building bigger and bigger telescopes. Probably don't have time to go through them all, but they're all pretty much similar to the James Webb, same technology, but using more segments, so you might end up with, instead of 6.5 meters, you got up to 16, 17 meter in diameter. But all of these things are going to be quite expensive because you're still launching all these mirrors. Excuse me. So this is another one called Louvois, which will be 11 meters, and this is actively being worked on now. So that's space telescopes of the future. The other interesting telescope to us in Edinburgh is not a telescope that doesn't look at electromagnetic radiation at all. It looks for gravitational waves. And gravitational waves were first discovered, been predicted for a long time, going back to Einstein, but were first discovered in 2015. And we're now trying to build a gravitational wave telescope in space. And in the audience, we've got Ewan Fitzsimons. Sorry about that. Who's the UK PI for the LISA hardware, which we're going to talk about in a minute. Gravitational waves emit from very, very powerful events in the universe, like black holes merging, neutron stars, supernova, and so on. It's actually a wave that travels at the speed of light. I'm running out of time, so I'll miss that. Okay, so how do you measure this in space? Well, the LISA program is to build something that's most amazing. It's got some fantastic numbers in it. So it's got 3 spacecraft, and they're separated by 2.5 million kilometers from each other. And in each of them, there is what's called a test mass. And I'm going to ask my assistant at this point to come and see. So this is a model of a test mass. The real thing's actually made of gold platinum alloy. So could you just pick that up carefully? God, what do you think about it?
This is rather heavy.
It's rather heavy.
Yes.
So this weighs, don't drop it on your foot anyway. So this weighs 2 kilograms, so it's very heavy. It's actually made of tungsten. As I said, the real thing's going to be gold platinum alloy. In fact, each one of there are 6 of these in the mission, and each of them costs about €1 million. So you put it back. That one doesn't cost that much. Anyway, so what we have is a system of these 3 telescopes that are flying around behind. You can sit down now. Flying around just behind the Earth in orbit around the Sun. in this pattern. And what we're trying to do is to measure the gravitational waves' effect on these test masses. So LISA to scale, if the Earth and the Moon's there, and we've got the spacecraft separated, you can see it's a lot further than the Earth to the Moon. And but the amazing thing about it is what we're trying to do is to measure changes in the position of these test masses to a very small amount. It's actually 10 picometers, it is technical, but it's about the same size, or it's a tenth of the size of an atom, which is incredible to think. So this is equivalent to something on Earth being able to measure the thickness of an A4 paper at a distance of 4.4 light years. So it's actually amazing. This it's science fiction, you would think, but it's actually really science. How does it work? Well, I don't think I've got time to explain this. I think you're going to have to go and talk to Ewan after it. But they've got these test masses that are in free fall, so they're totally isolated from the spacecraft and are just falling in space, and it means that they're very, very sensitive. So even the weight of a virus landing on this would be measured by the system, which is hard to believe. Some very technical and clever stuff going on. But the key part of it is an optical test bench, optical benches with all the optics on it, which are about this big, and they're being manufactured in the UK Astronomy Technology Centre in this test facility. And it's amazing to me that these things, which are going to be key to this project, which may cost €4 billion, it's going to be the biggest thing that ESA have ever built, both in cost and in size. And it's going to be done in Edinburgh again, so another fantastic achievement, hopefully. Right, so let's go back. Let's think further ahead. So those are the things that we know about that we're going to be building. The next things are going to be what we might build in the future. So we talked about lunar telescopes. This was the idea of, what's his name? Robert Richardson. I found this picture, but I have no idea where it came from. I've had it in a PowerPoint for years. It's obviously Russian, but the words say Mount Palomar Observatory 5-metre telescope. It obviously isn't that. It's obviously a telescope on the moon. So I have no idea where that came from. Other things are this sort of steampunk cover of a magazine, which looks like a telescope on the moon as well. But some real proposals have been made. Roger Angelo, who invented spin-cast mirrors for ground use, proposed something that would be basically a liquid mirror on the moon, which could be manufactured actually in space on the moon. And Peter Chen at NASA Goddard proposed moon dust and carbon nanotubes combined in some strange way. And he's made some prototypes, but none of these things have come to anything. So maybe the moon's not the best place anyway for an infrared telescope. Anyway, so formation flying is the next thing that's important. We talked about LISA. Ewan tells me it's not really formation flying because they're allowed to drift apart. They have to keep in alignment so you can see the lasers, but they can drift apart. But there were proposals to build formation flying telescopes in the past, an extra one called Zeus, a study that was done for looking at exoplanets called Darwin, which had sort of Herschel-sized telescopes all flying in formation. And there's this one that Antoine Leverrier has been talking about for many years, which is the most ambitious. This is talking about hundreds of telescopes, maybe 1,000 meters apart. And with that, he thinks you might even be able to image continents and clouds around an Earth-like planet. Okay, so my idea, though, that came out of a study we're going to talk about, is called Space Overwhelmingly Large Telescope. And the idea here is that if we take the James Webb Space Telescope and we think about the primary mirror, it's got 18 mirror segments. They weigh 40 kilograms each, so a lot more than that. But if we made a 100-metre one, it would have 4,500 segments and weigh 180 tons just for the mirrors. So we couldn't possibly launch that. It would be far too expensive. But the interesting thing is, the actual thing that does anything is just the gold coating. And on JWST, that only weighs 45 grams. A bigger telescope of 100 metres would weigh 11.5 kilograms, so it's not much. So you can imagine building something in space and allowing it to be very lightweight because you don't actually need to launch it. So there are people talking about robots in space to build stuff like this one. This is possibly assembling a telescope using segments. And the other way, though, is actually go out into space and manufacture things, maybe using additive manufacturing, which has been around for some while. This is building things up rather than machining things down. This is being used for things like aircraft blades by Rolls-Royce, so it's not science fiction. The interesting thing about it is that you can get very lightweight structures. So if you take a design like this for some sort of bracket and then optimize it, you can get much lower mass. Colin Atkins up at Edinburgh, up in the ATC, has been looking at making small mirrors using this technique and making progress, but it's not going to be ready tomorrow for big things. But there are some other technologies that might help. Okay, so this is a company in Amsterdam which has proposed building a bridge using robots and additive manufacturing. And the thing they do is to basically use some sort of arc system to build a wire, to make a wire that's computer controlled, and then program it so that it follows a path, and then you can end up with some sort of structure like this, which you may find is useful for building telescopes. They've built a bridge, which is across a canal in Amsterdam, which is rather splendid, but it doesn't look very lightweight to me. And somebody else it's going back one. So there's also an artist that's made a sculpture using this technique in Holland. There are other structures that may be very good for supporting mirrors. This is called a Voronoi structure, which is based on the sort of patterns you get on giraffes, but in 3 dimensions. And this could make a very lightweight structure as well. So next going to talk about how we can possibly use these technologies to build a giant telescope. So this is a study that I was involved in for ESA and the European Science Foundation. I missed that actually. But it also goes back to my friend Herman Noordung, where he said it's possible to make reflecting telescopes kilometres in length by placing at proper distances parabolic mirrors adjusted by electricity merely floating in space. So this is the kind of idea that I'm talking about here. And it was kind of inspired by what was called the Overwhelmingly Large Telescope, which was a proposal for a 100-metre telescope on the ground from ESA, which got descoped into the mere 39-metre telescope. So the idea of the space one is something similar, but in space without the structure. And I missed this bit because I haven't got time for it. So this is the concept. So you have a 100-metre mirror, which you build in space, and then you have another bit of optics, which is free floating in formation flying. And you build this mirror by some mythical means of additive manufacturing, so that you gradually build it till it's bigger and bigger, until it's 100 metres in diameter. And to do this, there's a potential idea is that we could have some sort of former, we call a mandrel, a metre in diameter, metre in diameter, build a coating on that, and then build a structure on the back of it. Now the shape is exaggerated. The real thing is actually only a fraction of a millimetre sag in the middle of the mirror, so it's a sort of size of a thickness of a human hair, so it's pretty much flat. Anyway, you build this up, and then you move your mandrel, and you build it up again, and you keep going until you've got this giant mirror. Sounds easy. It's not easy. Well, we've got an optical design though. So the design is based on a Gregorian telescope invented by James Gregory a very long time ago. So it's even more time travel. In St Andrews, it was never built, but it was the rival to Newton's telescope. And we're taking that same design, which has got 2 concave mirrors, and this is an optical design where the mirrors are nearly a kilometre apart. I won't go through it, but it does work. We can end up with perfect images from this 2 spacecraft system, and then we can make this great giant telescope. The only thing we've got to do is try and control the position of these 2 spacecraft. And the accuracy needed is fraction of a millimetre. It sounds pretty difficult, but actually at the end of November, ESA are launching this project, which is called Proba 3. And this is a bit like the thing we mentioned before about holding your thumb against the sun. It's an artificial eclipse of the sun using two spacecraft, held to something like maybe 2 or 3 times worse precision than we need for this SPIRE thing. So it's, that technology is actually being worked on now. Right, so this sounds all kind of mad, and maybe it is, but I managed to fool people enough that on the prompting of Paul Palmer, who was in the audience, I actually put this idea to what was called a moonshot program. This was an idea-generating thing put out by UKRI during the last government in order to take the place of Horizon Europe. Very fortunately, the government saw sense and agreed to go into Horizon Europe. So even though I got onto the sort of long list for this and went to present it in London, I didn't have to take it any further. So I was quite relieved by that. But somebody might do it one day in the next 100 years. Never know. You need all sorts of technology, which I can't go into just now. But there's a lot of things we don't know how to do, and some things we do know how to do. So when ESA and NASA are talking about technology, they have something called technology readiness level. So things start at TRL1 when they're just being analysed in the lab, and go up to TRL9 when they're ready for launch, and actually have been launched generally. So I think this one's actually about TRL-1 or maybe -10. It's a totally wacky idea. But so were the wacky ideas that Nordung and Obert had 100 years ago. So maybe it'll happen one day. And the reason you want to do it is to look at exoplanets. So we now have, well, this is something I used to put up, 10 years ago. When I put this catalogue up on the screen, there were 940 planets discovered, and now we've got 7,333. Now, this was last week. There are probably some new ones already. So there are loads of exoplanets, planets around stars outside our solar system. What we want to know is which of these are dead, like Venus and Mars probably, and which of them have got life, like Earth. And to do this, we now go back to this spectroscopy. So if we look at the spectrum of the atmosphere of Earth, it's very different from Venus and Mars, which are pretty much only carbon dioxide. And to do this, you can measure the atmosphere by looking at a planet that's going around a star. And as it goes around the star, if you look at the light, at some point, the light is actually from the star, it's going through the atmosphere. And when it does that, for that small period of time on that slope, you can... where is it? It's gone. Okay, it's going to come back again in a minute. When it comes back, during that period of time, you can measure the spectrum. And if you do that, you might be able to find signs of life, all these different chemicals in the atmosphere. I don't know if anybody would have heard it, but Lisa Kaltenegger has written this book called Alien Earths, which is a good popular introduction to planet hunting in the cosmos, and it was actually serialized on Radio 4 recently. But she leads the Carl Sagan Institute at Cornell, and she's come up with this spectrum, which shows what you might expect to see looking at an Earth-like planet from one of these spacecraft. And we think that you could look at actually something like 500 solar-type stars out to a distance of 100 light years using something like this SPIRE thing. And pretty likely you're going to find one of these that's got signs of life. We might even find them with James Webb Space Telescope or the 39-metre 100 telescope on the ground, but it's possibly not that likely. We'll see. What I'd like here is that during this group's also come up with the idea that if you were looking at the atmosphere of the Earth when there were dinosaurs on the Earth, there's a lot more oxygen during this period, much more oxygen. This makes it, if we were looking at a planet that had dinosaurs, it'd be a lot easier to detect. So I'm quite pleased for any 8-year-olds in the audience. We've got alien life, we've got robots in space, and we've got dinosaurs. So it's a full set. Okay, so this is the idea, that we end up with a telescope that could be 250 times more sensitive than James Webb. and give you a detection of a distant exoplanet 56,000 times faster, using this fictitious method of manufacture, which may be possible in the next 100 years. So some of these ideas came out of this study, so I've got to mention these people that helped with it, including Martin Colin from the European Southern Observatory, and some of the people that are in Edinburgh, one of whom is in the audience, I believe. No, he's not. Thinking of David Henry, not David Lee. Yeah, okay. Anyway, so that's it. I'm just going to put in a final plug for the open days at the observatory over the weekend, and of course at King's Buildings on Saturday. So if you want to know more about this kind of thing, go along to the open days at the Royal Observatory this weekend. You need to book to get into it, but it's very interesting and exciting. Thank you.
Well, thank you very much. You hit my inner 8-year-old perfectly, so thank you. I loved that. And it's a privilege to thank Professor Cunningham for his valedictory lecture and for all the difference that you've made to the School of Engineering in the last 7 years and beyond. So thank you very much for that, where I know that what you've done has been far beyond what was asked of you, and we got a feeling for that today, for how you've managed to inspire students and staff in the way that you talk, in your very measured way that you speak as well, and how thoughtful you are, everything that we would expect from a systems engineer. So thank you very much for that. And also everything delivered with a little twinkle in your eye too, so a bit of starlight. So thank you. And I loved how we looked forward to things that might happen in the future, to what telescopes look like, some science fiction as well, so comfortable offices, if you noticed that too. Will we ever see those? I don't know. And we're very grateful to all the time that you've spent with the School of Engineering and with ATC. So thank you. And this is now, congratulations for the formal conclusion as you approach that of a long, varied, extremely productive career. So we're going to wish you in a moment a very long, happy and healthy retirement. And please remember, the way that we do things in these lectures is we don't invite questions in public. Instead, if you have a question for Colin, please go to the reception outside. Do not take the liquid oxygen, take instead the alcohol. And take a drink as well, and go over, offer the drink to you, and then ask the question. Okay, so I hope you're not driving home tonight.
I'm not.
No, good. Okay, so please, can we all show our thanks and appreciation for Colin for this wonderful lecture? Thank you very, very much.